Enzyme kinetics expression where we have what's referred to as uncompetitive inhibition. The idea is that we have an enzyme reacts with a substrate to make a complex. This complex then can react with an inhibitor to make an enzyme substrate inhibitor complex. And the important thing here is this now is not active. So it's inactive for making our product. Only the enzyme substrate can react to make the enzyme again and a product. This last step is irreversible. These first two are reversible. And what we're going to do is derive a rate expression using the idea of rate determining step. And so what that means is we're going to assume the first step is in equilibrium. We're going to write the equilibrium expression for the reverse reaction for convenience. So we're going to write it what's referred to as the dissociation constant, which is dissociation of this enzyme substrate complex. Concentration of enzyme, concentration of substrate over concentration of the complex. Well, we're going to do the same thing for the second step. We'll assume this is also in equilibrium. I'm going to write a similar type expression. Finally, rate determining step. If this is the rate constant, the rate that we make product would be the rate constant times the concentration of complex. And so we need to write this in terms of measurable variables such as substrate concentration, inhibitor concentration, and enzyme concentration. Keep in mind, we've assumed this third step is irreversible because low concentration of our product P. So one other piece of information we need to now derive the rate expression is that the total enzyme concentration does not change. And that's the enzyme that's not in the complex plus the enzyme that's in the complex with the substrate plus the enzyme substrate inhibitor complex. Now what we want to do is make a substitution. We want to solve for the concentration. What we're going to do is end up with expression for the enzyme concentration, because we can substitute for this and for this from these two equations. So let me make that substitution. So I've made the substitution, but I can't yet solve for enzyme concentration until I make a second substitution, and that's substituting for E sub s, again using this expression here. Right, so I have the enzyme concentration. Let's go back and look at our rate expression. The rate that we're making product is K, and I'm going to substitute from this equation so that I have concentration of enzyme, concentration of substrate divided by Km. So the rate product formation is K. I'm going to substitute in for the enzyme concentration. Here's the substrate concentration. Denominator then Km times this denominator over here. Let me copy. And so essentially we're finished, but let's do a couple things. We're going to take this term and we'll call it Vmax. And so the rate product formation Vmax, substrate concentration, and in denominator we're just going to multiply through by Km, first term Km, and then we're going to factor out the substrate concentration, and so this becomes 1 plus inhibitor concentration over Ki. And so this now is our final answer. It's the rate expression for enzyme kinetics where we have uncompetitive inhibition. And if we compare it to the Michaelis-Menten expression, it looks similar, but so this is the Michaelis-Menten expression, but we have this additional term in the denominator, which is telling us the rate is going to be slower, of course, because of inhibition, but it looks similar form to the Michaelis-Menten expression.